So, we're almost done. Almost done. Chapter 4. What's after this?
Okay.
Rational functions. Now, why do we, let's see if we can analyze what this means. Rational. Do you guys see any base words in there or root words?
Rational.
Rational. Well, even within there's ratio.
So it's
What does ratio mean?
division.
Yeah, ratio means your division, fractions. So basically we're combining everything that you loved in chapter 3 with fractions, which you all love. And it's a perfect union of them all. Now why do we have fractions for usually? What does a ratio usually mean? The odds of you winning the lottery are 1,000,000 to 1. What does that mean?
1 in a million.
It's a comparison, right? So ratios come up all the time when we're comparing stuff. So for this class we have f of x equals p of x over q of x, where both of these are polynomials. Now this is how fun this section is. Remember all the finding the zeros that you had to do here? Now you get to do it twice. Where's your smiles at? Good. It's too early to smile. All right. So what can go wrong when you divide? So that's the main thing that you have to worry about. What can go wrong? So it's not a rhetorical question. It's what can go wrong?
You don't know how to divide.
You forgot how to divide. That can be wrong.
Reducing?
Reducing. But is that wrong?
Oh yeah, if you can reduce, you're gonna get it wrong.
So that's something that can go right. If you can reduce it, that's a good thing, because you made it simpler. What goes wrong? So let's look at an example here. What could go wrong? 1 over x. Right, the bottom can't be 0. What about something like x plus 1 over 2x squared plus 5x minus 3? What could go wrong? You guys see a general pattern here? Division by what could go wrong here? When you're dividing by 0. So you want to make sure, so this is where our domain issues come up. Domain is restricted to where the denominator is not equal to 0. So everything can go right except if you divide by 0. Okay? So what could go wrong here? If this, usually we just set it equal to 0 and then say everything but that. So my math lab will want you to put the answers like this. I don't want this one to be negative infinity to 0 union 0 to infinity. That's everything but 0. Well, what could go wrong here? Can we factor this? So notice that chapter 3, do you guys see how it already pops up? What were we doing in chapter 3 that you guys all loved?
Dividing.
We were trying to find zeros, right? Now you're lucky it's a second degree right now, but we'll do a 13th degree pretty soon. So, I gave them a 13th degree on Thursday, and no one did it. I made up the numbers too. It was like 27 million. Can we factor this?
Yeah.
So 2 times -3 is -6. Are there any factors of -6 that can give us 5?
I don't know.
6 minus 1, right? So this is 2x. Well, first of all, you know, since it's prime, it has to be something like this, right?
I know you don't like using the quadratic formula, but could you use it?
You can use a quadratic. Oh, you can always use it. Always use a quadratic. If you're lucky, you can factor.
Get the zeros and then go back up there and do the x plus 1?
What will be even a faster way to do this? You guys are gonna hate me now. You're gonna hate me even more, I should say. So this is plus, we need it to be a 3, and then -1. So let's review really how we find these zeros. I think that's how we do it, right? So let me take this part, which I can't. And then this is going to be, what, x equals 1/2 and -3?
Why is it 3? Isn't it 5?
It's going to be
Or, I mean,
it's going to be
6.
6 minus 1.
Oh.
You guys remember the double smile test? Oops. If you've never seen it before, you basically say like this, like 6 minus 1. That's 5. So let's review how to find some zeros. So I factored. Lulu suggested the quadratic formula. What's another way to find zeros? Calculator, right? So let's go to our. I'm gonna show you a trick that you've never seen before. And what am I gonna do to you on the calculator to find zeros? Remember, you can't forget this because we're doing this in this chapter.
Find the 0.
Right. How do I find the zeros?
Go to second.
Now this one is easy enough, but I'm going to show you something right now. So hopefully you guys are playing along. Plus 5x. You guys are going to love me. You're either going to love me or you're going to hate me after this. So zoom 6 to reset it, right? Okay, do I have any zeros? Yes. And the zeros look to be about 1/2 and -3?
Yes.
And I could find that by doing calc zeros, right? Is there any other way to find zeros? The table. The only problem is you wouldn't find the 1/2, but yeah. Now here's another way to do it. You guys ready for this? Some of you guys won't be able to do this, but hopefully most of you will be able to. If you have an older calculator, you might not be able to. You see this apps right here? Okay, we're gonna click on it and download Angry Birds. So, you're gonna go until you find Polysmilt 2 or Plysmilt.
Enter.
You guys see it? Everyone?
No. It's an older calculator.
Oh, then. Yeah, you can just watch us.
Would you push out?
I pressed apps. Apps is all I pressed. So for those of you who have maybe an older 83, you have an 83? So it's okay, you can still solve yours are like 7 ways to solve things. This is just another way to solve things. I'm gonna press enter. Now here's the thing, our program, there's now a program running on our calculator, so you can't just get out of it by pressing second quit. Now you see the polynomial root finder? Press enter. What degree is this problem here?
Two.
2. So I'm going to go to 2. And then you see the next right here? I get that by pressing F5. So now, can you guys figure out what I'm going to do now?
But do we have to put alpha F5 or just F5?
Just F5. Just graph, whatever, yeah.
Right there.
Yeah, you're good. Now some of you guys will have it lined up vertically. Some of you guys will have it this way, but it's the same thing. Just type in the numbers. And then -3. Oops.
So
So you're A1.
I got A2.
So this is A2 will be 2.
Okay. 2.
A1 will be 5, and then you'll have -3 for the last one.
Just like that.
Yeah.
Oh.
Okay. You see the solve right here? Press F5 or graph or whatever. And look, there's the answers. So,
Whoa.
yeah. This even does real answers too. Real, I mean, imaginary. So remember chapter 3 when I would say find all 5 zeros?
We could have done it this way.
Yeah, but then you wouldn't have learned anything. So now I teach it to you. Now that you appreciate the synthetic digit.
Now that we failed the test.
I know, right?
I'm screwed anyway. I can't even do it on my
When are you gonna pass the test out? You should do it now.
Huh? Do what?
Pass the test out now.
If I pass the test out, I guarantee everyone will be staring at the paper.
It feels like 5 minutes
Crying.
there.
To take it in.
break.
So I want to get it at the end so I can run away, lock my door,
Yes.
and be barricaded back there. All right, so now we have a super fast way of finding zeros, right? See, if you guys would have come to my office hours and asked, I would have maybe told you. Psst, here's a shortcut. The only problem with this is like when you have like crazy imaginary complex numbers, it's kind of weird. Anyways, oh, and then to get out of it, you have to press I don't know what, main, exit, or quit. I think you can download it though, Isabel. That's where you plug in your USB to the computer. And, you turn on this computer on the side and go boom. Then the dot matrix printers. It's not that old, huh? You know, the monitors that are green text on the black background. If you leave it on, like it burns and image on it. So, the good old days. All right, where are we at? So, we have a new function now. It's called f of x equals 1 over x. We're going to call this the reciprocal function. Can you guys see why it's called reciprocal function? Don't all answer at once, please. So, this one looks like now when you divide by a polynomial, things get crazy, right? They're no longer continuous, smooth, parabolas or W's or whatever. So that's what it looks like. The domain, what do you think the domain is going to be? Well, I already kind of did this problem on the last slide. Whenever you do a domain, ask yourself what can go wrong. In this class, there's 3 things that can go wrong. We'll just write this on the side. The first thing is division by 0. The second thing is square root of a negative. And the third thing is, we're going to see it in the next chapter, a logarithm of a negative. But the point here is just think about it. When I ask domain, the question you ask yourself in your mind is, what can go wrong? What can go wrong? You then go through this list. Do I divide by 0? Are there any radicals here? Are there any logs here? No. Is there a division? Yes. So the domain is when x, this one is easy enough, x is not equal to 0, right? Simple enough. Now let's look at the range. What y values can come out of here? So these are what we call asymptotes right here. You can guess which one is a horizontal. This is a horizontal asymptote, this is a vertical asymptote. Okay. What that means is that it gets closer and closer and closer and closer forever, but never touches it. Okay. So, what looks to be the asymptote here? What number can I never get out? What number never comes out of this function? So for example, I can have, so let's say my function, let's say it's a machine, and it's called 1 over x, right? And I plug in different numbers. Like let's say I want 1/2 to come out. What would go in so that 1/2 comes out? 2, right? If I plug 2 into this function, out comes 1/2. It's a reciprocal, right? What if I wanted 3 to come out? What would I put into it? 1/3, right? 1/3 goes in, flip it, 3 comes out. Is there any number that can never come out of here? 0.
0.
Right? 0. So that's basically what you're asking when you have a range. The range is what number can never come out. Another way we think of it, remember I used this example of we're flattening it, right? So we're saying, does this ruler touch the red graph? Yes, 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 no. You guys see that? It doesn't touch it at 0, so the range is not 0. Yes, 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 yes. And the same thing works with domain. Does it touch it? Yes, 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 yes. No. Yes, 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 yes. Yes? No? Yes? No. No? Says you can see the same word and just the way you say it means something different. All right. So that's the range. So the range is negative infinity to 0, union 0 to infinity. Okay. I'm gonna keep going on the same page. So let's think about what's the domain and range of f of x equals two over x. Now think back to chapter 2. Chapter 2.3, I think it was. What is this 2 doing to the function? What does it do to this original function right here? It's like me putting a 2 right up here, right? If you think about it, this is like 2f of x would be 2 of x, right? And what does the 2 out in front do? It's a vacuum. No. It's a
Vertex?
not a vertex. It's a very important thing.
There you go.
Vertical stretch, right? This is a vertical stretch. So this is a vertical stretch of the original function, right? So what that means is it kind of stretches it faster, whatever. Well, it kind of goes, it looks pretty much the same, except it's stretched. What is the domain and range of this? Now here's the thing, we can ask our calculator all these questions too, right? 2 over x. Graph it. Now some of you with older calculators who don't have the color TV, still watching I Love Lucy and black and white. Back when married couples slept in 2 separate beds. This is 2 over x. So what's the domain here? What could go wrong? Well, the same thing, right? You're dividing by x, by 0. Now when you stretch it, does it really change the range? No, because the 0 is still going to be 0. So this one is still the same. Now the reason I'm stressing these domain and range questions is because the final I don't write, but they always ask these questions. And so I'm trying to like stress them because they'll probably be on your final. They will be on your final. I've already seen it. So it's pretty hard too. I saw it and I was like, well, not for you though.
Okay.
The domain, well, the answer to both of them is negative infinity. Like I saw the final and I said, is it fair to ask a calculus question on this algebra final? And so I'll try to hurry up and get to calculus for the end of the semester. Psych. All right. Now what about 1 over x? That's not x. 1 over x plus 2. What's the domain and range? Now, you can solve this without your graphing calculator if you just think about what am I doing to my original function here.
You're adding 2.
I'm adding 2. Now let's describe that with translations. It's a or you can just
Vertical
say up,
stretch?
you can just say up 2. Vertical shift. This is shifting up by 2, right? So this means that now it gets interesting. I'm going to draw 2 right here. This is 2. And the function is just shifted up, right? So now it looks like this. Now some of your calculators, when it draws this, it'll draw it like this. It'll go. And the reason it does that is because it connects the dots. It doesn't know, hey, stop. Right? But if it does, just know that's what it's doing. Now what's the domain? Well,
Negative infinity and 2.
what's the only thing that can go wrong here?
It's a
0.
When x is, so I'm just going to put x not equal to 0. Now the range, if I squish this, right? If I use this ruler here, now at 0, it does touch the blue line, right? Where does it not touch the blue line? At 2, right? Well, it makes sense, doesn't it? Like, you're moving the asymptote up 2 also. So the horizontal asymptote, or the range, is, you could say y not equal to 2, but my math lab will want negative infinity to 2 union 2 to infinity. Like I said, you can use your graphing calculators to help you out. Okay. Now, that's basically 4.1. Pretty simple, right?
So it's mostly trying to figure out the domain and range.
Mhm. So chapter 1 would be harder if we didn't have graphing calculators. But then they say start sketching graphs. But guess what? We have graphing calculators. So. Rational functions part 2. So just like The Godfather, here the sequel is better than the first one. No one's seen The Godfather?
Yeah, it was.
Hmm?
It was.
It was, huh? It was one of those few movies where the second one was better than the first one. So what I'm going to do is I'm going to make you a deal you can't resist. No one gets these references, man.
Maybe you gotta use the accent, man. Come on.
I'll make you a deal.
There we go.
Marlon Brando. Have you guys seen that movie?
Yep.
Not the second one.
That's a
You
second.
gotta see the second one. It's way better.
Way better.
We should play it right now.
Yeah, that's what's
Yeah.
fun.
Throw it on for me.
Yeah. I won't get in trouble at all. I'm going to show you guys a movie. I think probably a little part of a movie later this week, but it's not going to be The Godfather.
Oh, man.
I saw a dead horse today in class. All right. So, asymptotes. So vertical asymptotes. We're going to define them formally now. Asymptotes are really good in life. You actually like asymptotes because you know what that means? It means stability. Okay. Let's say this defines all the arguments and the hardships that you and your husband or wife have, right? You don't want it to go down to infinity forever, right? You want it to kind of stable out sometime. So these are good things to look for when you do these types of functions. Stability. Is population stable?
Oh, no.
No. But actually it is. We're going to talk about that this year. Can we have exponential growth forever?
No.
So this is part of the next chapter, so I'm not going too much off on a tangent, but you can't grow forever, right? So the human population right now is like 6 or 7 billion, right? It cannot become 100 billion. It's impossible. Because if you do the math, that means like you start having like one person per square foot, after a certain point. So the human population has to go, like, it's exponential now. There's going to come a point where it becomes stable. And what that means is the amount of people live are the same as the amount of people that die. Now the question is, where is that? And if this is time down here, when is that? If we have 1 billion people today that are starving and in poverty, we're going to double the population within our lifetimes, right? There will come a time within our lifetimes that we have 10 billion people. Can we now have 3 billion extra people if we can't even feed 1 billion people today? Are we going to have enough gas and oil for them? Food? Money? So this is stuff that's some of the applications of this stuff, right? How about gas? Is oil finite or infinite?
No.
It's not infinite, right? Oil will run out. That's a fact. Because it takes like 100 million years to make oil, right? You can't just, oh, let's just make some more. Right? So once you use it all, it's gone, right? So what are we going to do to get around once the oil is gone?
Start walking.
Go back.
So,
Step back.
Wagons.
so I remember a professor once told me this. This generation may be the one where your grandkids will ask you, what was it like to fly in an airplane? Do you think we're going to have enough oil for airplanes in 50 years?
Probably not.
Right, we need something else.
Well, no one's investing on that, so.
We've already used more than half the oil that the Earth has. And we're increasing. Now we have China and India using oil. Instead of riding bikes, they're driving cars. Why not? The Americans do, why don't they, right? So, what's going to happen? So this is stuff that math, this is when it starts getting really interesting, especially chapter 5. It's looking forward. What is coming ahead of us? Right? All right. Does Tucson have enough water to double its population?
No.
Does PCC have enough electricity to run on a Thursday? Apparently not. All right. So if f of x goes to infinity as x goes to a, this is when it shoots off like that or like that. Okay. In science, they call these singularities. You don't have to know that, but if you're ever watching like a movie about the Big Bang or something, they mention the singularity. Basically what that means is you're dividing by zero somewhere. Like Mars decided to divide Venus by zero. I don't know how nature would do this. But no, but like, you guys heard of black holes, Big Bangs, all this stuff? They always happen at these singularities, like something happens that shouldn't happen. Horizontal asymptotes are if f of x goes to b as x goes to infinity. Now notice the difference here. The difference here is that if you think of x as time, here we're saying in a finite time, I shoot off to infinity. That's not good, right? Because that doesn't happen, right? You might say, oh, well, we won't say oh today. Now this is saying as time goes on, I'm stable. This is like a good thing, right? As time goes on, stability. So there's these famous examples in biology where you study coyotes and rabbits or something, foxes and rabbits. So if you have too many foxes, they eat all the rabbits, but then there's no more rabbits to eat, and so then the foxes start to die out, right? But then if there's not enough foxes, the rabbits take over, and then something happens, I don't know. The rabbits run out of food, and so then you need, like, there's a balance, right, between stuff. Like supposedly we need trees and bees. I don't know.
Yeah,
It's like,
we need
it's like a
trees.
conspiracy, you know.
Like all the time.
Especially the bees.
Yeah, of course we need bees. Now, does this look familiar? How many times did we solve this one? A bunch, right? Let's find the asymptotes. Now all we did before was find the domain, right? So the asymptotes, vertical asymptotes, here's the secret, are where the denominator equals 0. So we've already solved this, right? With our handy dandy calculator. What was it, 1/2 and -3? So that means when I draw this, I can put a -3 here and a 1/2. And I know for sure that there's going to be an asymptote here and an asymptote here. Because I'm dividing by 0 at -3 and I'm dividing by 0 when x is 1/2. Now what happens in between? Well, I don't know. So what do I do when I don't know? Just quit, go home. Calculator. X minus 1, x plus 1. I didn't even put x, put times. X plus 1. Now remember, you need parentheses a lot in this chapter. A lot of students mess up problems because they forgot parentheses around the numerator, parentheses around the denominator. 2x squared plus 5x. Remember, if all else fails, just go to Zoom standard, right? Just to reset it, Zoom 6. So you guys see how this looks? The asymptotes right here. -3 and 1/2. You can kind of see it here visually, but maybe it's a third, right? The only way to really know is you just solve it by hand. But we just found out that, I just already forgot what it looks like. Now here's a bonus question. Before I teach it to you guys, let's see if you guys can figure it out. Where is this going to cross the x-axis right here? What value of x is that? What does it look like it might be?
-1.
-1. Now the question is it -1? Why is it -1?
X plus 1 equals 0.
When the top is 0, the whole thing is 0, right? 0 divided by anything is 42? 0, right? So I know that this is going to cross at -1. It's going to look like this. And yes, you do have to sketch some of these graphs later on. Now here's a question. Is the horizontal asymptote, is this green line ever going to cross the x-axis? Like, is it always going to stay above it? Or will it cross? How about, will this one cross? How do I know for sure?
Is the range?
That's kind of part of it, but so let's use our Mexico, United States analogy. Here I am in Mexico, right? If I'm going to end up in the United States up here, what do I have to do to enter the United States? I have to cross the border, right? Now, do I ever cross the border here? How do I know for sure? Crossing the border is equivalent to finding the 0, right? Is there any other place where this is equal to 0? No. Like if there was an x plus 10 in here or something, yes, it would cross it again. It doesn't cross it ever again. So I only cross the border once. Now here's the thing about asymptotes. Asymptotes are like space portals. They can beam you from infinity to the other side of infinity. You can kind of imagine this as, all right, I'm not going to cross the border. I'm just going to go south. And I'm going to keep going south past the South Pole. and I just keep going around to the North Pole, and then come to the United States. You can do that, right? So that's kind of what this is saying, but it's kind of weird to think of it. All right. So the end behavior here is, it kind of dies out. There's all this excitement. You first meet someone, you go on your first date, you get married, you're on a high, and then you got a kid, and then what happens?
You run out of money?
Not really.
All right, maybe not for everyone. For some people, it goes off to infinity, into the sunset. You know, in the movies, like they always say, oh, it's romantic. You like right off into the sunset, right? But see, this is the way I think of it. All right. So first of all, you're on a horse, right? And it's the old days, and you're riding off into the sunset, and then the music crescendos. Oh, the end. Right, and it's like, these are like old movies, all right? It's usually cowboys involved, because who rides off into the sunset?
Right.
And then the credits roll, right?
Mm-hmm.
And everyone's like, that was so romantic. And then you know what I'm thinking? All right, now it's dark, and it's cold. You got no lights, there's no cars. You're out in the middle of the desert with the horse. Is that more romantic?
It's gonna get ugly.
Yeah, it's more. You might get lost.
Is
you
he
might.
alone?
Huh?
Is he alone?
No, usually right off into, like, you take the woman you love and you ride off into the sunset.
That's why I said it's gonna get ugly.
And now it's dark, you're gonna trip, your horse is gonna break a leg, and
You're thirsty, you're tired, you're cold.
mosquitoes are gonna bite you. That was back when they had malaria, dysentery, you know, drinking the water, Montezuma's revenge. Oh, you guys know why I'm single already. Just do the fantasy, play along. I'm realistic, though. So. All right, what's the domain and asymptotes here? Well, let's just find the asymptotes. Vertical asymptote. What could go wrong? Besides marriage and kids, what could go wrong?
You're laughing.
X equals to 0.
Yep, my ex is definitely a 0. Well, in this case, X is 3, right?
Yeah.
So we know that at 3, 1, 2, 3. I'm just being dramatic, I know. But I hope you all get married one day. I wish you many marriages. So, what else? Are there any horizontal asymptotes? Now, I'm not going to tell you how to find them. I want you guys to find them. Try to find them however you... Use all the basic skills I've taught you so far. So I haven't given you guys any formulas yet, right? But you know what a horizontal asymptote looks like, right? If you know what it looks like, is there some way to make a graph? Like, well, I just told you to make a graph, right? Let's graph it. The answer to everything, this graph.
Negative 1/2.
2x
Is it the negative 1/2 right there?
That's what I thought.
Well, the negative 1/2 is the y-intercept,
Oh.
right? Which is important. We're going to have to know that later on. But the horizontal asymptote is there a stability? What does this go to as time goes on?
It's going down.
As time goes on. Well, this one's going down and this one's going up, right?
Oh.
Well, technically they're both going down here, right? Because you always go from left to right. But does it look like there's a asymptote here?
No.
There kind of is. Maybe it might be hard to see.
Oh, wow.
But at 2, which of course the shadow disappears it, this never touches 2, and this never goes below 2. Now I'm going to show you how to calculate this by hand, but can you guys see it at least? You guys see that y equals 2 is an asymptote. What that means is if this represents something in life, population or your money or whatever it is, that y equals 2 is a stability point. Y equals 2.
Is that for the horizontal asymptote?
Yeah, the horizontal asymptote. Now, is there any way we could see a 2 in here?
We'll get to on the very left. What do you do with that?
There's a 2 here. So now let's think about asymptotes happen as time goes on to infinity, right? We don't care about right now, we care about in the end. Right? In the end, what's the human population going to be in 10,000 years?
Non-existent.
Probably 0, right? Probably be gone by then. In the end, how much money are you going to have in your bank account? That's me right here. In the end, how many kids are you going to have? In the end, I don't know, something. In the end, how many trees will there be? How many elephants will there be? Because you can't have a bazillion elephants, right? Mostly because bazillion's not a number. But, what happens in the end? Is there stability? Is there a nice, even answer? So what this means is we had to consider, now you study this a lot in calculus, but we're just going to do a little bit here. This is part of the chapter 2, so it's not tangent. Is end behavior. So you can kind of think of it as in the end. As time goes on, what happens? Watch out for that.
It decreases.
Right, well, so let's think of an example. Let's say we have 2x to the 5th plus x plus 1. Okay. Now let's look at the contributions of each of these terms to the total result. Okay. So let's say x equals 1. If x equals 1, then this is going to be 2 times 1 to the 5th, whatever. Now notice that the 1 and this one, like they're all pretty much equivalent, right? They're not that far off. This is 2 plus 1 plus 1 is 4. So these two terms have a big influence when x is small. Now, let's say x is 100. I'll go from left to right to left now. This is still 1. This is just a little, here's $1 every day, right? Here's $1, here's $1. This one is saying, all right, you know what, I'll give you $100. I'll give you a little bit more every day. Every day I'll give you $1 more. Today you get $100, tomorrow you'll get $101, $102. What about this one? Well, another way to write this is 10 to the second power, right? So this is 2 times 10 to the second to the fifth, which is 2 times 10 to the, is it 7th power? 10th power, that's big, right? That's 20 billion. So the final answer is going to be 2 billion and 101, right? Or 20 billion, right? Now, let's think about this. If you have $20 billion, even if you have this much money, does $101 really matter? Do you really care? You're like, give me my $20 billion, okay, you can keep the $1 bill, right? And as time goes on, these are going to matter even less and less and less. In some sense, you can approximate this from that one. If I say how much money you're going to have when x equals 1,000, I can say, oh, 2 times, what's that going to be, 10 to the 15th. This isn't going to matter much. I mean, what is this? If you wrote this in scientific notation, this would be 2.00000001. Very insignificant, right? So this is what we mean by, in the end, it doesn't really matter. So, you guys know that one? Probably not, because I don't have a good voice. But, is it Lincoln Park? Lincoln Park. So do you guys see how the leading term really dominates? Right? This is Donald Trump money, or supposedly, right? This is me right here, like right here. This is me today. On Friday's payday, all right. I'm 100 in there. So the main point here is, as time goes on, this is what matters. Okay. Let's say if you're a country, and every generation you just add one more person. We're like, okay, one more person to the next generation. And then you're a country that says, we'll grow 1 each year. And if you're a country that says, look, we're just gonna reproduce like crazy, you don't really care about, that small little country. So the point here is that in the end, you say, cut the BS, what matters? Yes, I left my socks on the ground, I'm sorry. Yes, I forgot to wash the dishes. But I love you, right? My love is exponential. This is what matters, right? Or what's the vice versa of this? Yes, you bought me flowers. Yes, you bought me a car. But then you slept with my sister, right? That's what matters, right? It's like, so the leading terms matter. See, life is math. right? That's what it is. The leading terms matter. Now I know some of you guys might say all terms matter, but we're not going to get into that right now. They dominate. So when we go back to this previous one, I'll just copy and paste it over here. Well, you know, we'll just look at it. Do we really care about this 1 and this 3 as time goes on? They're not growing, but here these are growing, right? So in the end, actually we'll copy it. In the end, this, as x goes to infinity, this whole thing, the leading terms matter. You guys see that? When x is a billion, I don't care about that one extra penny, you know. So then I can say, well, what does this go to as x goes to infinity? This goes to, if I got your calculators, 2 divided by 1 is 2, right? What was the horizontal asymptote here? 2. You guys see that? Let's take a little 5-minute break, and then I might hang out your test too.
I just wanted to know. Yeah.
So the leading term. So finding Nemo. Oh, it's still frozen. All right, finding asymptotes. So vertical is always the easiest. Can't spell it. Asymptotes. Let's find Toto. Asymptotes. Set denominator equal to 0, and then x equals a is going to be your vertical asymptotes. Where a is the 0. So remember, this is chapter 3, right? Finding zeros, finding zeros. Horizontal asymptote. So take the leading terms. Only. Okay? And then you simplify. So basically what happens is, let's say this is degree n, and this is degree m. There's 3 possibilities if you compare n and m. So if you take n and m and m and n and then n and n.
Can you go a little? Yeah, that would be done.
So there's 3 possibilities. Either n is greater than m, n is equal to m, or n is less than m. So when n and m and n is n m and m, then m and m and m. So n is greater than m. Okay, this means that the top is growing faster than the bottom. Now this is the analogy I'm going to use here. A piece of pizza, a pizza pie, right? A piece of pizza with M&Ms, and So if the top is bigger than the bottom, so the top is the number of pizzas you have, all right? The bottom is the number of people you have to share it with, okay? The question is, how much pizza are you gonna have in the end? Well, if the top is growing faster than the bottom, then I'm getting more pizzas. I'm getting pizzas faster than we can split them up and eat them, right? So what's going to happen to the number of pizzas I have?
You didn't get more.
Right. So there's no. That's all weird like that. No, no horizontal asymptote. It goes to infinity. Or it dies to infinity. So I got so many pizzas that we just can't eat them fast enough. So I tried this experiment for my class last semester and I gained a few pounds. So the things I do for my students. Except it was Christmas time, so it was tamales. Just joking. So now let's say the bottom. Let's say the bottom, I have a, like let's say I'm making a pizza once every hour, okay? But every hour, more and more and more and more people start coming in. Faster than I can make them. Okay? What's gonna happen to the amount of pizza everyone gets? So we can also think about it as, let's say I just have one pizza and there's more and more and more and more people, right? How much are you gonna get? A tenth, 100th? Because remember, this is gonna go on forever. It keeps growing. This room keeps on growing. But I only got one pizza. Well, it sounds like Little Caesars, right? I only got one pizza. How much pizza is everyone gonna get?
None.
Not a lot, right? And we're gonna cut the pizza smaller, and before you know it, you're just gonna get like a little Parmesan sprinkle. And after a while, I'm just gonna blow the aroma on you and go. And that whiff of pizza is how much you get.
You get 0.
So y equals 0 is the asymptote. Does that make sense? This is how funny I am. This is how many jokes I tell. As time goes on, it just goes down to 0. They're not, the humor's not being replenished. Now, that's the interesting case. Is there's a balance. Okay. Let's say I can make 2 pizzas an hour, and 4 people come in every hour. So that means each person gets half a pizza or something. But then the next hour I make 2 more, and then the next hour 4 more people come in. So this is something you'd want in a restaurant, right? You'd want some kind of stability where I'm not just making stacks of pizza and no one's buying them. And I didn't run out of ingredients. So this is gonna be the ratio of the leading coefficients. I'm a lot happier and I'm talking about food. Not about love anymore. So this is what happens. So for example, that problem, and I'll just write it down here again. So for example, this one we already did, 2x plus 1 over x minus 3. This rule right here works, right? This is 2 over 1 equals 2. So getting the horizontal asymptotes, Mr. P here. I know you guys were looking at me weird, like, where's the P at right there? All right. So this is actually really, really easy to do. This is the easiest part of a test. If I say find the horizontal asymptotes of x squared plus 1 over x minus 2, you don't even have to graph these anymore. What's the degree of the top? 2. What's the degree of the bottom? 1. This rule applies, right? There's no horizontal asymptotes. Because this is going to grow faster than it can. I'm making pizzas faster than I can eat them. So no horizontal asymptote. Now, we're going to use all our knowledge and now, how many times have we seen this today? This is like the third time at least, right? Now what we're going to do is sketch by hand. Now, the reason the sketching by hand is important because your calculator is really hard sometimes to see all the asymptotes and everything. Your calculator is good to check your answer when you're done, but sometimes to get the exact answer, you have to do it this way. Now we've already seen how this graph looks like, right? So let's try to build it from scratch. So first of all, let's find the vertical asymptotes. Well, I'm going to break this up even higher level. We're going to do zeros. I want you guys to have flashbacks of last week. Root, factor, zero. X-intercept. So, the zeros of the numerator well, these look easy now compared to the ones I was giving you on the test. How do you solve that? I don't know. Are you guys so shell-shocked that no more zeros?
And it goes -1.
Right, x equals -1. These are going to be zeros of the function. So I forgot to call this f of x. That right there. Because if the numerator is 0, then it's 0 divided by something. 0 divided by something is 0. And then you get 0, and then the 0 divided by 0, and then the 0, 0, and then m, and n. Just waiting for you guys to reply. So you guys like, this teacher's insane. All right, the denominator. The denominator, we have already solved this like 6 ways today, right? We factored it, we graphed it, we could have quadraticed it. The Polysmith app. We found that the answer was 1/2 and 3. -3. These are the vertical asymptotes. Now there's one more 0 that we're forgetting about, and that's the y-intercept. The y-intercept is actually really, really easy to find if you just realize this. The y-intercept means x equals 0, right? If x equals 0, that's gone, and that's gone. So what's left over? 1, -1/3. Do you guys see that?
Wasn't it 1/2?
We're not talking about the horizontal asymptote. We're talking about the y-intercept. The y-intercept is when x equals 0. right? So when x equals 0, cool. When x equals 0, this is gone and this is gone, right? So I just have 1/3 and it's a negative, right? Ah. So this becomes f of 0 is 1/-3. So the y-intercept is 0, -1/3. When I plug in 0, this term is gone, these terms are gone, and I get 1/3. Right? Now, I need the, as Isabel mentioned, the horizontal asymptote. The horizontal asymptote is end behavior. Remember I told you this should be the easiest thing to find? Because all we look at is the we look at the what do you guys all want to do when you're done with college? Get your what?
Degree.
Your degree.
Oh.
I hope so. So you take the diploma of the numerator, the diploma of the... So what's the degree of the top?
1.
1. What's the degree of the bottom?
0.
So n is less than m, right? Therefore, what's the horizontal asymptote? Y equals 0. It's the last one, y equals 0. Since n is less than m. So what I'm really doing here is I'm just analyzing everything I can about this. Now, let's see if we can put it all together. Okay. The first thing I found was it goes through 0 at x equals -1, right? So here's -1, just hanging out, chilling. And it is 0 there. The graph will go through 0 at that point. Next up, vertical asymptotes, 1/2 and -1/3, or -3. 1/2, -3. Now notice I don't put in all the other points just because I like to keep it simple, right? Yeah, I know there's a 0 here, whatever. You know. These are horizontal asymptotes. Okay? The function's either going to go off to positive infinity or negative infinity. There's a singularity. There's a black hole. Light does not leave. The y-intercept is x equals, so I actually do need to know 0 because I'm going to graph this point here. So something like this. I should use the same color, black. Let's go black. So then the point here is -1/3. Now remember some of you guys said it was a -1/2 earlier?
Mm-hmm.
It's actually -1/3. Now I'm not really drawing this all to scale because I'm running out of space here. But the point, it does go through this point. Now that's actually important. And the end behavior is y equals 0. So now remember, the end behavior just means at the ends. It can cross 0 in between. Now you look at all this and you say, well, what the heck? How can I finish this off? I know how the middle has to look like. Let's think about this. This cannot go off to infinity this way. Why not? Okay, why can this not go like this to infinity?
It's a negative.
Because then the next point is down here, right? I'm in Nogales. And then someone calls me, now I'm in Magdalena. And I don't cross the border again. Well, I might as well just keep going. Let's go to Panama. Right. So I know how the other side has to look, right? This can't, why can this not go back down right here? Because if it did, it'd have to come back up. You'd have to say, all right, I'm in Tubac, I'm in Tucson, now I'm back in Nogales. So this has to go like that. It has to go to infinity. I know going this way has to go positive, because here it went negative. Now what about the rest? Well, this is where you do a test point. This is where you do a simple test. So what's the next biggest number? What's the next biggest nice number bigger than 1/2? 1, right? All you care about is positive or negative. Here's the 0. So I'm going to plug in 1 here. 1 plus 1 is
5.
I don't get me calculator out.
carry the 1. It's 2. But all I care about is the sign, right? So the top is positive. If you prefer 2, it's 2 or it's positive, whichever one. The bottom is going to be 2 plus 5 is 7. Minus 3 is 4. That's positive, right? 2 divided by 4 is positive. So what that means is that if that's positive right here, it ended up being like 1/2 or something, right? I don't care. I just know that it has to look like this now. It has to go to infinity, but it's not going to go to the negative infinity. And it never crosses the x-axis because I already found all my zeros. This was my only 0. Now what's the next nicest number over here? -4. Let's plug in -4. -4 plus 3 is plus 1 is -3. That's negative, right? -4, that's going to be 16. 32 minus 20 is positive, right? Let's do that again. 32 minus 20 is 12. Minus 3 is 9. It's negative over positive. Negative. Now you can put this in your calculator if you needed to, right? It's going to be negative something. The point is that it's negative. Thus, it has to look like, well, it doesn't look like that. It looks like this. Now, we've already graphed this before, so we know that this is the right answer. But this is how you would, you've shown all the important stuff that happens here. There's an asymptote here. It eventually dies out. There's a lot of commotion in the middle, but in the end, the love withers away. This is everything, right? You got kids at home, terrible twos. Eventually they move out, right? Well, eventually, hopefully. Your mom's all like, you should listen to your instructor, right? Of that moving out part.
My brother was doing that.
And then it's quiet. right? All is quiet. Asymptotes, the zeros, you got all the important stuff here. Now this one was, we already did it before. Now let's do one from scratch. Sketch by hand. So basically you're going to do this template over here. So I'll give you guys some time to do that. Actually, I want to start. The sketching, you can do it. We already did it once, so let's move on. Let's try to get into the next chapter. So don't erase it all. Save it for your fun time tonight. Rational equations. Because chapter 4.4 is something different, so I want to at least keep it this topic. So x plus 2, 2x plus 1 equals 0. Now, what do you do when you have fractions?
Give up.
Give up. You multiply by
Reciprocal. Conjugate.
The denominator.
No, you don't need to conjugate here. You guys are high powered right now. Do the rational zeros theorem. You multiply by the LCD, right? So I'm going to multiply both sides by so here I'm going to get, well actually, this cancels out, right? That cancels out, that cancels out. X plus 2, and what do I have over here? Now we look at it right away and we say, let's categorize. What type of problem is this? What degree?
1.
1, right? This is linear. Can you guys solve linears? I don't know. The last test. Of course you can, right? All right, I might as well just keep solving it. Just in case. So x equals 1 is the answer. 1 plus 2 is 1 plus 2 is 3. 2 plus 1 is 3. 3 divided by 3 is 1. It worked. Okay.
Can you go back?
Yeah, just hold for a sec.
I'll just keep going down here. How about that? Now remember, this could also be thought of as a zero solving problem, but it was way too easy. We could just solve it, right? But normally, you would set everything to the left-hand side and then find the zeros. But like I said, it was too easy. Here, What's the LCD here?
There's 3 of them.
So this is x minus 2, this is x plus 2. This is x plus 2,
X minus 2.
x minus 2.
So that's the LCD.
This is the LCD right here. Now I would normally let you guys have time to do this, but just because time's running out, I'm gonna guide you through it a little quicker. Now here's another way to think of these problems. Now this looks complicated, right? In one step, it's gonna look like easy. You're gonna be like, come on, Ron, let's give me a hard problem. So another way to think about this is, what does this need to become complete?
X plus 2.
X plus 2, right? So I'm going to have the x times x plus 2. What does this need to become complete?
X minus 2.
You guys see how I'm getting these? What does this need to be complete?
Nothing.
Both of them?
Well, it already has both of them. So it needs none of them. Now let's categorize this type of problem here. What degree is this going to be?
Second.
Do we know how to solve quadratics? Yes.
Sure.
I hope so. So x squared plus 3x, and I'm going to do a minus 8 over here. So minus 10. So like I said, I'm just going to go a little quicker just to do more problems. Now, you always have to check your rational answers. So -5, you plug it in, blah, 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 it comes out, right? What happens with the 2 when you plug it in? 2 divided by, what's 2 minus 2?
0.
0.
Can I divide by 0?
No.
So can equal 2.
It can't equal 2. Now keep in mind, I've been giving you guys multiple choice. Now the reason I don't mind giving multiple choice questions is because you'll have something like this. And doesn't any one of these sound like a good answer? Right? Well, I got -5 and 2, but I'm too lazy to check. I'm gonna think that Morales hates -5s today. You know, you just check. That's all you gotta do. Any one of these is valid. You could get everything right and get 0 credit on it. That's the trade-off for multiple choice, right? It's all or nothing. I think we'll leave it there today because it's 2 o'clock. So.